start recording, I will introduce the speakers. Okay, so it's my pleasure to introduce Alejandro Martin Lobos, who will give a talk today on anisotropy and spin fluctuation effects on spectral properties of Yu-Shiba impurities. And let me tell you a little bit about his vita. So Alejandro got his PhD. Oh my gosh. Oh, sorry. Got his PhD in Bariloche in the Centro Atómico. For those of you who know what's going on there, and it's one of probably the best place in Argentina. I don't know if I'm allowed to say that. Physics. And then he, after completing his PhD with Armando Aligia, who has been working on strong correlation effects in magnetic impurities mostly, right, for a long time, and he's well known. He moved to Geneva. And he switched a little bit fields. So he worked on one-dimensional systems, quantum dissipation, and that's where we met. This was around 2008 or something like that. Yeah. We ended up writing a couple of papers together, and eventually we have been in touch. And after 4 years in Geneva with Yamarki, with Thierry Yamarki, he went to Sankarta Sharma in Maryland, right? So he was there at more or less around the peak of this Majorana.
Yeah, just right after Majorana.
Right after Das Sharma proposed this. Well, he was one of the people who proposed these Majoranas in quantum wires. And after this second postdoc, he went back to Argentina, where after some short period in Rosario, he eventually went back to Mendoza, where he's from. Okay, that's where he is coming from this time. And we are quite happy. Unfortunately, today is his last day here. And okay, if you want to talk to him, I think you can try to catch him in the afternoon. So anyway, without further ado, I just give him.
Yeah, thank you very much, Miguel. It's a real pleasure to be here talking in the IPC seminar. I want to thank the institution and also Miguel for this kind invitation and for all the support in this place. I've been having a wonderful time. Unfortunately, this is my last day here in the institute. So, but in any case, we can stay in touch if you have questions or comments or whatever. I would be very interested in having your feedback of these results, because I have never had the chance to talk to experts in the field. So I would be very, very interested. So let me give a brief. Sorry. These things have time. Okay. Okay.
This is my fault, probably.
I'll give a brief outline of the talk, just for you to know where we are during the talk. I'll be giving a short introduction on Yu-Shiba impurities, magnetic impurities on superconductors. This is probably something that you know much better than I, but I will, for the sake of completeness, I will talk a little bit about what is Yu-Shiba impurity. Then I will present the work, this theoretical framework part. I will present the results and then the summary and the conclusions. So let's start. So the story about Yu-Shiba impurities is actually the story about a competition at the local, at microscopic level, between a magnetic impurity and the electrons in the superconductor, right? So on the one hand, you have the interaction between the impurity and the electrons, which so the impurity tries to bind the electrons through for instance, an exchange potential. And on the other hand, you have the pairing, which tries to bind the electrons into Cooper pairs. So these two interactions compete with each other for the ground state. And so this is something I borrowed from the review. And the result of this interaction is actually a complex competition between these two ground states actually gives, as a result of that, there are peaks which appear in the subgap region in the superconductor. And so this story started in the 60s with the works by Yu-Shiba, Yu, and Rusinov, very seminal works, in which at the level of this Hamiltonian, they assumed that the impurity is a classical object. So if you do this approximation is very nice, because all this Hamiltonian is exactly solvable, and then you can have exact results. And one of the important results is the fact that you can analytically know where these peaks will appear in the subgap region. And it has this very compact expression here that you can see here. So this energy is the energy of these resonances, these delta peaks, which are known Shiba peaks or Yu-Shiba-Rusinov peaks. And the alpha parameter is a dimensionless parameter that quantifies the interaction between the impurity and the electrons in the superconductor. And a few years later, it was clear that this as a result of this competition, actually there are two ground states in the low energy region. So two states that compete for the ground state. One of them is an even fermion parity ground state, which is adiabatically connected to the BCS ground state. So this axis here is you can say this is the alpha parameter. So for alpha 0 is actually this point is the decoupled interaction, the decoupled impurity, and this ground state is actually the BCS ground state. But as you move forward, there is another state which is an odd fermion parity that eventually crosses the energy, and at this point you have the phase transition, and this point is exactly the point where alpha is 1. So this is a very short picture, a short story about classical impurities. But then we can complicate the problem by introducing quantum fluctuations and considering a quantum impurity in connection to a superconductor. And then you have actually a much more complicated many-body problem, because then you have quantum physics which competes with superconductivity. And this has been studied by many people with a lot of methods: decoupling of the equation of motions, interpolation schemes, slave particles, energy, perturbation in U, Monte Carlo, and probably more methods that I have no idea. But then the overall picture is something that you can summarize in this picture here. Let's assume that the quantum impurity is a spin 1/2 impurity, and then what happens is that as you increase J, so you start from a doublet, which is the unscreened impurity, because of the presence of the gap, you don't have electrons near the Fermi surface. And then this impurity, which is now a quantum object, is actually unscreened. So then you have a doublet ground state. But at some point, you cross, you have a critical point at which this quantum physics start to come enters into the picture, and then you have a singlet ground state. So this is a doublet singlet quantum phase transition, which using some results from NRG occurs exactly or more or less at this point. So TK around 0.3 times delta. So this is more or less the overall picture from the theoretical point of view. But let's see what happens at the experimental level. So there has been very interesting results from STM, starting from 97, where I think was the first time these Shiba states were observed. But then the experimental techniques have enormously improved, and now there are much more. So all the experiments have much more resolution, and even this quantum phase transition has been observed in very nice experiments with organometallic compounds. So all these peaks are, so not these peaks, but these peaks are Shiba peaks, Yu-Shiba-Rusinov peaks. So very nice. So this is a very interesting thing. But in recent years, there has been even more interest in all this area because of the proposals that that eventually in these setups, if you put these impurities into and you form a chain, you can form a topological or you can induce a topological phase if this spin chain has a certain tilt on the order parameter, on the orientation of the order parameter, right? If this has, for instance, helical order, in principle, the theoretical results predict that you will have essentially a Majorana chain. So a topological superconductor with Majoranas at the ends of a ferromagnetic chain or spiral chain. And some of the experimental results, which started in this year, 2014, sort of led to think that actually there are signatures of a putative Majorana peak in this zero bias peak at exactly at the Fermi energy. And after this work, there has been many other works sort of confirming this prediction. And I have not followed this area very closely, but okay, this is a very interesting thing. I'm not very familiar with what is the actual what are the latest results on this, but this is actually very interesting. So, but let me point out a few questions that appear at least at the fundamental level. So the thing is that many of the experiments are interpreted in terms of the classical picture that I showed you before. So many of the things that you observe have been fitted or have been interpreted in terms of classical impurities. But the thing is that quantum impurities are actually quantum objects. So what happens when the impurity is a quantum thing? Okay, so you might say, okay, why don't apply one of these methods that I just showed you? The thing is that it's not that easy. And from a fundamental level, it would be nice to have, so there is a large gap between the classical approximation and the fully quantum methods. So is there any semi-classical approach that allows you to think of these spins as semi-classical objects? This is one thing. So something that can, describe the crossover from the classical to the quantum regime. And in a more practical aspect, some other practical aspects, the thing is that quantum impurities on surfaces are very complicated things. So you have typically higher spins, so typically up to 5/2, for instance, in transition metal elements. Anisotropy, single ion crystal fields, and a lot of non-ideal situations that in an experiment they appear, and all these interactions make the problem much harder. So how to deal with realistic spins? That is the question that I will be addressing in the rest of the talk, and how to include, for instance, other effects, like, for instance, the temperature. So this is the context in which we started to work in this system. So let me see how I'm doing with that. So I will present what we did. And this is largely the work of Alejandro Andrade, who was my postdoc at that time in 2019 when we worked on this project. And now he moved to Colombia, his original hometown in Universidad del Cauca in Popayán. And the idea was to come up with a theoretical framework which was capable of describing all the intrinsic complexities of quantum spins, at least in the weak coupling limit. So this is an ambitious goal. So we started with this idea. So the point is that we wanted something that could be able to describe quantum fluctuations, anisotropies, the temperature, and other interactions, for instance, or effects, the presence of other conduction channels or many conduction channels in the superconductor, magnetic fields, etc. So this is the idea. So let me start from the theoretical model. And so we're working with this Hamiltonian, which is what I showed before. So the superconductor. I will be assuming that the band, so the normal band, is electron-hole symmetric, which is it's not an essential approximation, but is useful for simplifying some of the results. Then the quantum exchange coupling is this thing, which we can divide into a classical term, let's say the classical Ising interaction, and the spin flip part that, of course, will give rise to quantum fluctuations. And for the anisotropy, I will be taking this very simple term, but it can be complicated with other different types of anisotropies. There is no intrinsic complications to apply this idea, right? So electrons will be two-dimensional, and an important simplifying approximation is that delta will be taking as constant. Whereas we all know this is something that depends on temperature, but in order to simplify the theory, we will restrict this to temperatures which are lower than the critical temperature, and we'll be taking this delta as a constant. So one of the most important objects I will be interested in is the Green's function. So this is the theoretical object I will be addressing. And because the problem is a superconducting problem, what you need to compute is not a single Green's function, but actually a Green's function matrix, which is this Nambu Green's function matrix composed by the let's say the normal part and the anomalous Green's function, which is something like this. It's a correlator which takes the C or C dagger correlation. And if the superconductor is a pristine thing, you don't, if you compute the unperturbed Green's function, this is something which is analytically known, very well known. So it has let's say the normal part and the particle component and the whole component. And if you take the density of states, this is something that gives a very well defined coherence peaks with the gap there. So this is something very well known. This is easy to obtain. And in the wide band approximation of the conduction band, this is the local Green's function. So the Green's function at, let's say, the origin has a very simple expression. So this is just the unperturbed part. But now we want the full Green's function. And in order to obtain this Green's function, I apply something which is called the equations of motion method. I will not be giving technical details, but it's something that you obtain by taking the dynamical equation of these electrons and then putting them back into the definition of this matrix here. And what you obtain is something very well known, is this expression where, okay, this is the unperturbed part, and this matrix here is the so-called T matrix. So the T matrix contains all the information or all the details of the scattering between the impurity and the conduction electron bands or the superconducting electrons. And it has this form where it is actually a matrix of these correlators, which are composite correlators. So each one of these operators is a spin operator times an electron annihilation or creation operator, right? So it is a complicated expression, and it is actually an exact expression. So if somebody gives you this T matrix, essentially this person is giving you the exact answer. So there are no approximations in this expression here. But of course, it's something that you don't know how to compute. That's the problem. It's a formal exact expression, but all the important things are hidden here, and you have to come up with a method to compute this. So in our work, what we did was to conceive a certain decoupling scheme for this correlator as eta, where eta is one of these annihilation or creation operators for the electrons. And so this is the Fourier transform of this imaginary time correlation, which is something which is so well known. It's a very concrete expression of these correlators at time tau and time tau prime. And the idea is that at least in the weak coupling regime, this decoupling makes sense, because if this was 0, so this would be exact. So the dynamics of the spin and the dynamics of the electrons would be completely uncorrelated. So so the idea is that starting from this point near a weak coupling limit, this should make sense. So if you do that and then go back to the expression of the T matrix, the nice thing of this approximation is that it gives a closed form for the Green's, so for the T matrix, into a product of the Green's function, so the electron Green's function, which is something the object we are interested in, and this Matsubara or these correlators for the spins, for the uncoupled spins, and in the weak coupling limit, it would be a good approximation to replace this thing by the unperturbed spin correlator. So this is something that in principle you know how to compute. And for instance, here this will be the dynamics of and the exact form of these correlators would be given by this Hamiltonian. But as I said, this can be as complicated as you want. So, and the good thing is that both quantum and thermal fluctuations will be kept alive in this method. So you will not be making the classical approximation here, right? So that's the main point. The bad news is that this Green's function appears inside this sum over the bosonic Matsubara frequencies. So it's not a simple problem how to extract this thing out of this sum. And just a few, let me just make a short comment. There are many decoupling schemes which have been tried over the years, right? Especially in the Kondo problem. And one of them is the so-called Nagaoka decoupling method. This is similar in spirit, but different, because what you do in the Nagaoka method is to make a decoupling which is asymmetric. So you put all your spin operators on one side. Well, it's a technical thing, but just for those of you who are interested in this technical aspect and theoretical aspects, it's different from this Nagaoka decoupling of the equations of motion. And the main difference is that here you keep the dynamics of the spin operators. In Nagaoka decoupling, you just take a static correlator of the spins. So let's take a look, because this is very important for what is next. Let's take a look of the unperturbed spin operator. So this is something which is computed in this form. So the problem has SU2 symmetry. So the only correlators that can appear are SZ or S plus S minus. So those are the only two which will appear by symmetry. So the SZ correlator is something which is actually static. So it's just dependent. So it depends it's a delta. It's proportional to a delta function in Matsubara space. So it's proportional just to the zero component of the frequency, and actually has this form. It's very simple. This delta are just the difference in energy given by this anisotropy landscape, and Z0 is the partition function, very simple expression, and the S plus S minus correlator, S minus S plus, is the dynamical part. Has this simple form. So if you replace these two expressions into the original equation of motion expression, now you get this sort of complicated result here, but you can see what is the actual mathematical task. This is something that you want to obtain, and this is something that is the same thing that appears here. So this is an integral equation for the G matrix. How to extract this from this the sum is the mathematical complication. So by assuming this particle hole symmetry in the band, and by taking the SU2 symmetry of the problem, you actually realize that in terms of this sum or difference of these Green's functions, you can decouple this. So this is a matrix equation, right? This is a 4-element equation. So you can simplify all the expressions into scalars. So in terms of this sum or differences, you can obtain this. This is exactly the same equation, but now it's much simpler because it's a scalar integral equation. And this is one of the most important results, at least from the theoretical point of view. So the thing you want to obtain is this, but it appears here and it appears here. How to solve this equation is what took us most of the time in this project. So the point is, one thing you can do is to discretize, so obtain this discrete complex frequency. So eventually you will be interested in the retarded Green's functions, which will be the same as taking the complex frequency Z as omega plus E epsilon, where epsilon is a very small imaginary part. But the theory forces you to take all the replicas, which are shifted by the Matsubara bosonic frequencies. So you can discretize your imaginary axis and take these discrete frequencies and construct a vector. So it's an infinite vector, which is located here in the complex plane, and the k component of this vector is just this thing, the function evaluated at this discrete frequency. And then you can define a kernel, which is this part. And then you can turn this integral equation into a matrix linear problem, right? So the thing you want here is here, but it also appears here. And in principle, if you could invert this equation, then you would extract the object you want. And eventually, you just take this element and you discard all the rest, right? So that would be, and for every omega that you are interested in, you have to repeat the process. That's the idea. But still, this is an infinite matrix problem. How to invert something which is infinite is numerically is not, of course, it's not possible. So what you need to do is to make an approximation here. It's not an approximation in the sense that you can take the asymptotic properties of Green's functions and actually make this sum. You define a high energy cutoff, let's say, and then for all these Matsubara frequencies which go from here to infinity or from here to minus infinity, you can actually do this exactly, this sum exactly, by giving this form for this asymptotic form for the Green's function, and then you turn this infinite sum into something. So this L max is the maximal Matsubara frequencies from top on the bottom. And then you have an extra component, an extra contribution that comes from this cutoff. But this is something that you can put into a computer and just extract the G's. So this is a very simple, very direct way to obtain the Green's functions. And the point is that there's a very important comment here on the accuracy or on the method itself, because this Lmax is inversely dependent on the temperature. So if you want to go to very low temperatures, this becomes very hard because you need to take a lot of Matsubara frequencies in this sum. So this makes the matrix more and more larger and larger, let's say. But you can do it with reasonable parameters, and then you can extract the density of states. I don't know if this is clear, but this is the density of states. It has two peaks inside the gap. And then if you change, for instance, the anisotropy, this gap, these resonances shift with the position, with the value of the anisotropy, for instance. So this is just to show you that this is something that works. It's not very hard to obtain. And a sweet spot in which this can be evaluated and in which gives reasonable results is within this region. So this is the same restriction I was telling you before, because the gap is a constant. You have to take temperatures which are lower than the gap. But because the method becomes very hard at very low temperature, you have to take temperatures which are higher than this, for instance, this cutoff. But within this region, you can move. And if you take a particular experiment, and for instance, this experiment here, which in this experiment we're using lead as a superconductor, then you are in this regime. But this is within the experimental range, which is very, very, very nice. So,
Alejandro, just one question. So in this graph there, so if they have a finite lifetime,
yeah, it's an artificial lifetime, just to see the peak. But yeah. Thanks for the comment. I was forgetting saying that. Yeah, this has been artificially broadened just to see the peak. So before jumping into the full resolution of this integral equation, let me give you something that comes for free. So imagine you are in the classical regime. So J perp is 0. So all the thing you have is just the Ising part of the Hamiltonian. Then that means that you have to neglect that part. And if you see, this is actually diagonal in Z, in frequencies. So you can directly obtain the Green's function in that limit. And this gives you a denominator, and the poles of this denominator exactly gives you the classical result. This is just a sanity check. There's no new result. This is something that you expected. But it is interesting to see that despite the method being perturbative, it is exact in the classical regime because of this this integral. So because this is a self-consistent thing, you can consider it as a self-consistent, or what is it? Sorry, as a self-consistent expression where you have to take this and replace it here and again and again and again. It actually gives much higher powers in J. So it's not just the second order perturbation theory, right? So this is, as I said, this is a sanity check, but it's very nice that appears almost for free.
So this will be also the temperature dependent, right? Because the alpha that you have there depends on this expectation value of a Z square, which is
exactly. Well, that's something that I will talk about later. This is something very important that I wanted to discuss with experimentalists. Another interesting result. This is a little bit more interesting, actually. So imagine you are in a regime where the anisotropy is much smaller than the temperature, or 0, essentially 0. Then you will be in the isotropic limit, right? So no anisotropy. And in that limit, this correlator, just by looking at it, it is clear that this this correlator, the S plus S minus. So this correlator, this is of course something which is static. But you can see the dynamic correlator becomes static in the isotropic limit because delta, which is proportional to the anisotropy, goes to 0. But if you take delta to 0, this is something that vanishes unless unless for all Matsubara frequencies which are different from 0, this is something that vanishes. But only at omega L equal to 0, this is something that gives you a finite result. And this finite result is this one. So all the other contributions vanish. So it becomes, so despite being something which is dynamic in general, in the isotropic limit, it becomes static. And then you can, again, you are in this case where you have something which for all omegas which are different from zero, you have to discard all these contributions. And then you get something which makes a lot of sense, actually, because if you sum sz squared and s plus s minus squared in the isotropic limit, you recover the correct s times s plus 1 factor of s squared. This is just nothing but the average of s squared, which is the spin correlator, right? So what we get for that expression is another peak, which I don't call classical now, what I call Shiba or Yu-Shiba-Rusinov, which has this other expression, which is different from the classical one. And it's interesting to take the expansion in 1 over s. And you can see that these two are related by this part, where this is a power of 1 over s. And of course, it has higher powers. But this is interesting because one of the main arguments using classical or by which you can justify the classical limit is because you take the limit s towards infinity, and then you are happy and you can sleep at night because you say, yeah, I'm in the classical spin regime. But this is not fully correct in the sense that this is a very slow decay. So here I have plotted this result as a function of s. So this is, of course, very unphysical because I'm taking s as a continuous variable. But just those, so these points are in principle the physical points. But you can see this approaches the classical limit very slowly. So for any reasonable value of the spin, you can be very far from the classical value. And this is something that has been known from energy results. Yeah.
A small question here. Like you say that it's not the classical limit, but I mean, from experimental point of view, you just change the alpha parameter.
Yeah.
And you have the classical limit.
Yeah, it's as if you were renormalizing the classical the alpha.
Yeah. So at the end, you don't have like a realistic number, but you can do all the physics of.
Yeah, of course. So if you renormalize your parameters, from an operative point of view, it's the same, but conceptually, it's very different.
Yeah.
It's very different. And this is something that CePdSb has discussed in this paper. This is a very nice paper where he computed high spin energy calculations. You can see here there are very unrealistic spins, but just for the sake of illustrating this point, you never reach the classical limit. So you approach this limit very, very slowly. And actually he's fitting this with a curve, which is 1 over s to the power 1.1, which is very close to what we have analytically. So this is something for us, it was very nice to obtain, as I said, very, very easily. It's just almost for free within this framework. So this was very nice. So the main message of this paper was that the classical nature of the spin is not given by the large spin, but by the size of the spin, but because of the anisotropy. So anisotropy is what makes spins classical or not, but not the magnitude of s. This is something for me was very nice and very clarifying.
Can you apply this thing also to the limit of alpha equal 1 and see the quantum phase transition?
In my case,
yes,
no. this is the bad side.
Yeah.
I will come to this point later. But you see here, I have extrapolated. This is probably the point. This is the critical point. But this is exactly the point where our method fails because we cannot recover.
10 minutes.
Fine. We cannot recover all the Kondo correlations because we have completely neglected them. So near the phase transition, or of course in the strongly coupled phase, you cannot trust the results. But at least in this region, I would say it gives very reasonable results. And okay, so then let me go into the full resolution of these integral equations. And let's take, just to start from somewhere, just the regime of large anisotropies. So this is larger than the temperature. So you have this Hamiltonian. And then in this axis, what I'm so in these figures, what I'm showing is the position of the Yu-Shiba peaks as a function of the anisotropy for a particular temperature, which is the lowest temperature we could attain with reasonable, numerical effort. I'm drawing the position of the Yu-Shiba peaks as a function of D, the anisotropy parameter. I'm starting from the isotropic point. You can go into the easy axis region or in the hard axis or easy plane region. And of course, in all this part, so as you make D larger and larger, you go into the classical. So this is this dashed line is the classical limit. So you recover the classical results if you make an isotropy larger or larger. This is exactly what I was saying before. So you go into the classical limit. Of course, the way in which you approach this can be you can go faster into the classical limit or not, depending on the size of the spin, right? But this is something which is systematic, either with semi-integer spins or integer spins, you get the same physics. But if you go into the other direction, what you tend to do is to penalize, so you favor low spin configurations. So this means that in the integer spin case, you go to the zero, so the impurity which has a spin 0. So it decouples immediately, decouples from the superconductor and goes to the, so this is a peak that will meet the gap, so the edge of the gap. But what is interesting is that in the semi-integer case, you don't reach the decouple limit, and this is because you have degrees of freedom which are kept alive. So eventually you always converge the spin 1/2 limit, right? Because you have at least 2 ground states which are degenerating energy. So all this, so this physics is completely different. And another thing we did was to study the crossover, and this is something that you were pointing out, Miguel, that there's something that I'm not an expert in experiments, of course, as you might have noticed, but there's a belief that the Yu-Shiba peaks are temperature independent. I've heard this, or I've read in different papers that this sentence, right? Yu-Shiba peaks are temperature independent. But this is something I want to rethink, or I want to discuss, because this is something that we don't observe, and it becomes very clear in this regime as you go from high anisotropy to low anisotropy in terms of these parameters. And this is the most interesting regime of parameters because you have all the interactions there fighting with each other. So anisotropy, quantum fluctuations, and thermal fluctuations. And the way to see that is that if you now make the same, you make the same plot, but instead of putting here D, you put T, so the temperature. This is something that experimentally might be very hard, right? Because you don't want to change the temperature of the cryostat, I imagine. But if you did, what I'm predicting is that this would be, so you will find these curves where from here, so you start from, from a very anisotropic limit where essentially you have 2 ground states. So let's imagine this is an integer spin. So you have maximal spin configurations which are favored in this regime because you are a very low temperature. So it's very hard to climb this mountain to go from here to here. But as you increase the temperature, this will be easier and easier. And because this is the thermal average, as you were pointing out, the scattering with the impurity will be different. And as I mentioned before, in the high temperature region where T is of the order of the anisotropy, you will be recovering the isotropic limit. So this is a completely different regime, and you will be exploring a different range of of values. Of course, if you had no anisotropy at all, this would be the complete isotropic point, which is temperature independent. Yeah.
How would this change if you change delta? Because delta will go smaller and smaller as
Delta
you
will
increase the temperature. So the energy of the Shiba will also change because it depends on delta.
So
how realistic is that the energy is changing?
Right. So this, as I said, this you shouldn't trust these results here in this regime because this is unphysical. But in this part, at least in this part, because this is normalized by delta, so it is in principle a reasonable regime for the method. And this is of course normalized by delta. So at least up to half of this plot, you will see the same plot. Okay, so I'm just finishing. But something that I found very interesting is that despite the fact that there are no plots like this, but for me it would be interesting because it would be like some test for the method. I found a sentence in this paper which is suggestive and at least goes into the direction of the isotropic of recovering an isotropic regime at high temperatures. So in this paper, which is the same paper I've been showing before, what they compute is the scattering of the electrons with the impurity, and so they compute what is called the effective temperature, which I think is the broadening. I honestly have it is not very clear to me what is this line here, but maybe you know better and you can explain me. But it is essentially the broadening of the zero energy resonance or the Kondo resonance. But what they say is something very suggestive. What they say is that interestingly, so this is the effective temperature against the experimental temperature. So they make something of this sort. So they change the temperature of the cryostat to take this curve. So this is why you have very wide error bars, I imagine. So it's not very easy to do. But interestingly, the deviation starts when the thermal energy surpasses the anisotropy energy of 0.33 milli-electron volts. Apparently, the thermal scattering diminishes the effect of the magnetocrystalline anisotropy. This is something which is consistent with what I am saying here. It's not exactly the same. You shouldn't compare these two because it's a different magnitude, but at least it goes in the same direction, right? So that's it. That's the story. Let me summarize. So what we did was to come up with a semi-classical approach to describe spectral properties of Shiba impurities. This is a weak coupling method with possible applications to some of these setups with organometallics because those are weakly coupled. So that the idea is that this is a weakly coupled system. As I said, this is not applicable to the screen quantum phase or near the quantum phase transition, unfortunately, but okay. This is a price to pay. But this is a simple description for the unscreened phase. And it allows to include many of the realistic effects like single ion, anisotropy, spin fluctuations, temperature. And you can also introduce other effects which I haven't done, like magnetic fields, conduction channels, etc. So there is still room for this. And I'm making this bold prediction that actually the Shiba states are temperature dependent if you are in typically all these surface, so these adsorbate systems or these organometallic systems have a lot of anisotropies. So if you are in this range, at least it should depend on temperature. So that's it. Thank you very much. I will have more.
There have been quite a few questions, but of course we have a few more minutes for some extra questions if you haven't. Yeah.
Comment on the factor you incorporate in your theory about the finite. It was on some slide.
Is it factor?
where you take into account the cutoff energies.
Right, this
And
is,
do you have any comment between the classical and the quantum?
this in this part.
Yes, yeah, exactly.
So this is, I mean, I don't have any comments on the physical side. It is like this is more like a mathematical step in which so this is a trick. Instead of using your numerical resources or your computer resources to compute very large matrices, you can introduce a cutoff. For us, this was a reasonable cutoff, beyond which you change this. So beyond which you can introduce this asymptotic asymptotic expression for the Green's function. So the thing you want to know is exactly this. But the good thing is that at very large frequencies, all Green's functions behave like this. So you can take this into account to perform this Matsubara sum exactly. So this is beyond this point. Once you made this assumption, you can completely integrate all the rest of the Matsubara frequencies. So this is a term which appears here. And then the thing is that we check that if you move this cutoff, your results shouldn't change,
Right.
because this is just it's a trick. But in principle, all your observables shouldn't change, and they don't change. So after a certain point, they don't change.
Yeah.
I have a question about the effect of the anisotropy on the energy of the Shiba, because I thought there shouldn't be a shift on the energy of the Shiba depending on the anisotropy. And I'm thinking that when you do the calculation of the density of states, right, you are connecting even parity state with an odd parity state, right? But as you are separating the spin part and the electron part, you're actually only taking into account the anisotropy for the even part and not for the odd part. So the energy shift that you are seeing, is it actually like realistic to say that it's changing with D, or only the even part is changing, but then the difference in energy shouldn't change?
So this is a very important point. I honestly can't answer you with a short answer. But you see, in the classical, in the classical case, you also do that, right? Because you also connect the even states with the odd states.
Yeah.
And this is an exact result. So whatever you do in this method, so what I'm trying to say is that even if you don't see them explicitly, you do have these two ground states somewhere in the equations of motion method. It appears here. So even though you don't explicitly see the ground states of the even part or the odd part, they are there because it's giving you the correct answer. So what I'm thinking is that when you turn on the spin flip part and the anisotropy, you still have these two ground states. So you are still connecting these two. So I think this should be valid, even when you have these two other interactions, so these two other effects, the spin part, the spin fluctuation part, and the anisotropy.
But is it because you are claiming that this is only working for the weak coupling regime?
Yeah.
And my understanding is that it is working because in the weak coupling regime you can decouple spin and electron part, but in the odd state, ground state, you cannot do this. But you are calculating now the difference in energy. But you are only calculating the effect of the anisotropy in the first energy, not the second. Yeah.
No, this is something I would like to test. Actually, that's what I say.
That's experimentally.
No, but even within theory, for instance, I would be interested in checking how good is this approximations with for instance another method like NRG. This would be very, very interesting too. So within theory, you can test how it's now. So how you have more work now.
All right. Yeah. I think we are approaching one, so maybe it's time to close. If you have any more questions, maybe you can ask them privately. If you agree, maybe we can finish here. So, well, let's thank Alejandro for a very nice
¿Qué tal?
Bueno, está muy interesante.
Sí, sí, muy potente.
No habéis intentado mirar estados fuera del gap, ¿no? O sea, los
No, no
picos
hemos
fuera,
intentado, no hemos
lo
intentado,
podréis,
y tampoco.
pero lo podréis sacar.
Sí, sí, se podría sacar, incluso.
Fuera del gap, tendréis excitaciones, ¿eh? Muy bonito, ¿eh?
Sí, incluso estos estados, thermal states would be also possible to study. We didn't do because at this point right after that this pandemic started and we completely shifted, and then Alejo moved to Colombia, and it was like I discontinued this time. But it would be interesting to see if there is
One experimental question that perhaps I didn't grab something. So when you have anisotropy, you in principle see two peaks. Two Shiba states.
two Shivas,
right?
right? But
You're plotting here only one.
okay, so two Shivas,
quantum model.
you mean
In the classical also.
In the class.
But yeah,
But which
when,
kind?
when
What?
you take into account tunneling, like you see the second Shiba when you do tunneling.
Okay,
and
so you just
then
you,
split
okay, yes.
the-
Okay. So since that you just consider the first one.
Yeah,
right? So if you have direct tunneling into the superconductor, or what are
no,
those?
if you do the tunneling,
In this paper from Hatter, actually, what they see is 3 peaks.
Yeah,
which
but those are thermal peaks, right?
no,
or not?
no,
Okay.
they are direct transitions. So,
Okay,
so
okay.
essentially you see the splitting of the Shiba, because now you can go from the ground state to all the, you have a
Right.
spin-one multiplet, right? And you can excite for the 3 of them.
Right, but then yeah, okay. So you are in the
These are outside the gap or
No, inside the gap,
Inside
and also
the
within the
gap.
single side model. So when all of this
Yeah,
is splitting
single
with
side.
J is the
Yeah,
same
yeah,
thing.
yeah.
only works for a small anisotropy, right? If it's big, it's going
No,
to
if
go
it's big,
out
goes out.
of the gap. Yeah.
But if this is small, and which is the case, right? In your case, well, you look all the anisotropy value.
But I was thinking,
I have to check that because that would be an important test, for instance. Yeah, I don't know, but
For D smaller than delta. So.
D is smaller than delta. Okay.
another thing you can try, maybe instead of temperature, is to crank up quantum fluctuations by putting a magnetic field perpendicular to the anisotropy axis, because that will increase the quantum fluctuation.
Yeah,
And that should have an
completely
effect
possible,
which
yeah.
is similar to temperature in a sense. So
But I will-
temperature is hard, but I mean, of course, the magnetic field will also decrease
Right.
the gap, right? But if it's parallel to the surface or whatever, it's probably
Mhm, mhm.
not so bad.
But yeah,
And
regarding
that-
the splitting, that would be something very important. I haven't looked for other regimes. So maybe these peaks are hidden somewhere, but I don't know.
And actually doing the measurement of the temperature for Shibas is not too complex, I think. It's something
No,
that
for
we
us it's
could-
not.
Yeah,
not
it's
complicated.
something that we could do.
Yes.
I mean, the complex part is that the gap is changing and it's a little difficult to see where
Right.
Shiba is at a certain temperature. But
Yeah, but this is how to extract the
Yeah.
change in the
Yeah,
energy
it's
of the
not-
Shiba
it's not
from
trivial,
the
I
change
imagine. Right.
in the
Yeah.
gap size, right? And yeah, that might be difficult, right?
Yeah.
But if you're at low enough temperatures, you can basically take constant.
yeah, I mean, but I don't know. I mean, we are starting from 1 Kelvin, so it's not the, we have
Yeah, but-
4 Kelvin, I guess.
Yeah,
so
but
it's not-
his question is actually very important, and this is something I've been thinking of. And
I mean, the parity of.
yeah, because this
parity
is connected,
selection
I think,
rules.
to the question of the splitting, because if you can describe correctly the odd parity states, then you should recover the splitting.
Yes.
And I don't know if this method is correctly capturing, the odd parity.
No, I think that we need to.
Because
This is something I would-
splitting of 2 types depending on which regime. You can have the splitting in the ground state spin,
Right.
because you have a spin 1 in the ground state, and there depends on the Boltzmann population. This is how they structure
This is
temperature.
thermal. Yeah, this is completely thermal.
And you can have you have a spin 1/2 and 2 channels in 2 orbitals, and then the excited state is spin 1 in a triplet, and there you can have the 3 transitions.
Yeah.
And there the 3 of them should have the same line with the same amplitude.
That's all. No, in the of course, if you're in the weak coupling regime, you don't have 3 peaks, it's 3 Shibas, right? You only have 1 because the splitted one is the.
If you are
even
in
one.
weak,
Yeah,
So it's
at certain
This is
oh,
the big-
temperature, yeah.
you have a higher temperature and population.
Okay, so then they are thermal.
This is what I was saying. I think this is what we haven't tried that because again at this point there was no interest at all in
What you have.
studying at higher temperatures. All these results are at the lowest temperature we could get. So at least
You're transitioning to the even parity
But this is something I can
But
check.
that's-
I can just put find a temperature just to check if there are more.
Or look for a spin combination that you have actually
Yeah, I
multiple
mean, they don't know,
states.
they don't know.
I think in this paper from
It's
CePdSb
just
also they have these
so-
diagrams that they can see many.
Yes, I
Multiple
been
excited
studying
states.
this paper, yeah. And then my recollection is that at this low temperatures, they don't see the splitting. So it's just, you just go from one ground state to the other ground state.
Yeah.
Yeah.
You need temperature to explore the other ones. But,
Which in all the experiments we have temperature.
that's the point. Well, that's one of the points. Right?
Yeah,
You have to come up with some method that allows you to put temperature in some way, right?
Very nice.
Yes, hard to populate.
Exactly. That would be another thing.
I will, if I ever, if I can, take this project again, I will let you know if I see the splitting. If you see something in your molecules, well, that would be very interesting.
But I think what he said is true to put microwave field also because something that we are also attempting now and pretend to populate the ground state population. That would be actually also
Very nice, very nice.
Very strong regime. Yes.
Right, you
Strong
so you will be targeting which transition you want to,
in principle, yeah.
which state you want to populate. Yeah, that's very nice.
Great. Thanks for coming.
Thank you for
Yeah,
the
thanks for
talk. Thank you
coming
for
for the
the
question.
invitation.
Hopefully he will come back.
Yes.
But we have a logistics.
Now he has the
problem to solve, which
GIPC
is,
stamp, he will be.
Yeah, that it's very hard to get accommodation in San Sebastian. It's a nightmare. And if you come from Argentina with all these problems to transfer money, it's been a
Oh, yeah.
Well,
I mean, the pocket is not valuable to transfer money.
ask the people of the Italian house. Seems like you have to be, a millionaire with all these stamps on your passport or something like that. To get,
It's weird that there are now people that they charge you for some percentage, but they do this work, like transfer money.
Yes. A colleague of mine is doing it. So they send dollars to Uruguay, then they buy bonos del Estado argentino. Then in dollars, they
separate them.
exactly. Then they transfer it to Argentina and they sell it in pesos. Another way around.
Oh my God.
And this is official. So there is now.
It's a legal thing, right?
It's a legal thing.
It's
So
not
there is a
illegal,
value,
it's legal.
Legal, and there is a value of the dollar conversion using this pathway.
Right.
Oh my God.
Together with the blue and all, they have also this pathway.
Oh my
It's very funny.
Wow.
So if you want to invent something in Argentina, they will be invented for sure.
Creative. Very creative.
If there is a hole, in the legality, it will.
Yeah. Good. Yeah, thank you.
Bueno, chicos, muchas gracias por
Bueno,
todo.
no, gracias,
Oye, no sé si te veré.
Bueno,
Buen viaje de vuelta
gracias.
y ya, nos veremos.
Bueno,
espero que vaya a Mendoza, te doy un toque.
Listo, nos vamos a una bodega.
Acabaré por allá.
Sí.
Bueno, cuando vuelva,
Sí,
intentaremos que vuelva seguro.
Además, te interesa tanto de esto.
Sí.
Muy bien.
Sí.
Nada, se vas al final.
Sí.
¿No?
Debe estar todavía.
Con la boca abierta, debe estar todavía.
Puedo decir que lo dejé con la boca abierta, pero
Sí.
no por eso.
Bueno, la foto que has tenido aquí, Nacho, es impresionante. Te dejaste con la boca abierta.
Espero que no tenga Instagram y se le ocurra subir una foto así.
Bueno, pues nada.
Muchas gracias por venir. Vamos a ver si podemos por ahí.
¿Esto lo dejo así, Miguel? ¿O hay que
Puedes, no sé, el pendrive te lo has sacado.
El pendrive ya lo tengo, sí, porque
Vale, entonces, claro, voy a enviar Carmen, ¿vale?
I would like to learn the theory of it.
You are nasty. I didn't know you.
Yesterday.
Yeah.
Okay, your team. Okay, sorry.
I didn't go necessarily because I was not doing just noise. Because I think this people as implemented for features. Just before. Actually, already have some simulations. Milan is leaving after Munich, right?
He already.
Yeah,
Somebody. Well, that's if
We can meet after lunch.
Okay, because I have a friend, I know someone that is
maybe
working.
for so much money, you can take them with you.
Yeah.
We were talking about.
No, we're to Milan, you said.
No, Munich.
Munich. So you can go.
This is a big position.
I was like.
It's the same.
¿Qué sabes que yo tenía?
Nos vemos en la copa. In Milan. So I had some results. So I did the ones like non-periodic, and I'm now calculating the one that's periodic.
But the leads are finite size.
Finite size. Yeah, and I'm now doing the periodic one.
Okay.
I found out, okay, you can just do periodic boundary conditions.
But you're doing only transport.
I'm now doing calculating, that's your state. If you want, that's your state.
Yeah, of course, it's STEAM. STM, there's no transport. We go to them between the islands and say, well, it is there.
Nice. You're sitting here.
DMC, fourth building.
Oh, we can meet there.
Yeah, should I come to Aragona or here?
Yeah, sure.
I mean, you have a laptop, yes?
Yeah, I have. Yeah.
Then we take the meeting room.
Yes, okay. I have a presentation, we can show, you can see the data.
Yeah.
Okay.
Yes, I can go to it.
Aren't you doing experiments?
Eh?
I should love data.
No, when you have so much data, and you don't know how to handle it, it starts to be a little bit.
You should use
Maybe like
AI.
for-
Yeah, but he uses AI, not in the lab, but
You should like train him
Yeah.
to like write some code that puts your data into the right.
Oh,
No, because my boyfriend is experimental, it's not
Yeah.
this.
What's that?
He
Oh, yeah, right.
takes the data from the lab,
No,
write a code for him to handle that, and now
Yeah,
he's
yeah.
not writing this code. It's
no,
does.
he does the same best, one of the same.
Oh, okay.
Whatever, and
Okay, so maybe, yeah, we go, maybe check how we can go somewhere, right? Because I have to leave around 4, so. Nastia, should we meet to discuss
Yeah, sure.
around 3? Is that okay?
Yeah.
Because I have to leave around 4.
Vamos. I don't trust it.
Oh, no, you should not practice,
No.
but it's just a good welfare in your box for your data. Scared.
It's not the it's so yeah. To get the type value parameter for the so I can do yeah.